Hi class, let's do an example of problem number 7 on the homework. And in this problem what we're going to do is we're going to take a look at how air temperature changes as air ascends and then descends. And so we're going to take this air over a mountain and check out what happens to the temperature of the air. First as we take it up over the mountain and then as we bring it back down over the other side. So this is a little bit different in that all I'm doing is I'm giving you the temperature of the air. And so the temperature of the air at the surface, at the base of the mountain, is 10 degrees Celsius. Okay? Now we're going to force this air to rise. And the other thing that's a little bit different than other problems is I'm not giving you a mixing ratio, not giving you a relative humidity. All I'm telling you, a given at the start of the problem, is that the lifting condensation level, the LCL, the level at which you have to lift the air to reach saturation, to reach condensation, occurs at 1,000 meters. Okay, and so let's not worry about relative humidities, mixing ratios, calculating relative humidities. I'm telling you that the LCL is at 1,000 meters. So we're going to get this air to rise from the base of the mountain up to 1,000 meters first. And so when we do that, we have to ask ourselves, as this air rises, okay, and pressure decreases, the air expands, the density decreases, and the temperature is going to decrease. Is that temperature going to decrease at the dry adiabatic lapse rate or the moist adiabatic lapse rate? Well, the answer to that is, okay, is the air saturated down here at the surface? Okay, well, it isn't, because I'm telling you that the LCL, the lifting condensation level, occurs at 1,000 meters. Now remember, what happens at the lifting condensation level is relative humidity reaches 100%. So I'm inferring that down here at the surface, the relative humidity is not 100%. The air is unsaturated at the base of the cloud. Okay, and so therefore, this air is going to cool as it rises at the dry adiabatic lapse rate. Okay, so let's take a look then and see what is that air temperature going to be at the 1,000 meter level. Okay, and so the temperature of the air at 1,000 meters will be the temperature of the air at the starting point, okay, at the surface, 10 degrees C. It's rising, so it's cooling, so we're going to subtract, and we're going to subtract the dry adiabatic lapse rate, 10 degrees C per 1,000 meters. Okay, and we're going from the surface up to 1,000 meters. Okay, and so that's a 1,000 meter change in altitude. Okay, so there we go. And so the temperature at 1,000 meters will be 10 degrees C minus 10 degrees C per 1,000 meters, and we're going up 1,000 meters. So 10 degrees C minus 10 degrees C. And so our temperature at 1,000 meters will be 0 degrees Celsius. Okay? So temperature at 1,000 meters is 0 degrees C. Okay. Now, this is where the LCL is. So this is where the clouds start to form, and these clouds we're going to assume, okay, make it all the way up to the top of the mountain. So we'll draw our clouds in there. All right. Now, as we go from 1,000 meters up to the top of the mountain at 2,000 meters, again, the air is going to rise. Pressure decreases, air expands, density decreases, and so the temperature decreases. Is that air going to decrease at the dry adiabatic lapse rate or the moist adiabatic lapse rate? In this particular case, we hit the LCL, the air is saturated, so as the air continues to rise, it is going to cool, but it's going to cool at the moist adiabatic lapse rate. Okay? And so now we can calculate what the temperature of the air is. at 2,000 meters. So temperature at 2,000 meters will be the temperature at the starting point. Our starting point here is at 1,000 meters. That's 0 degrees C. Okay, it's rising, so it's cooling, so we're still gonna subtract. We're going to subtract now at the moist adiabatic lapse rate, which is for our latitude 6 degrees C per 1,000 meters. And we're going from 1,000 meters to 2,000 meters. Okay, so that's a 1,000 meter change in altitude. Okay, so our temperature at 2,000 meters will be 0 degrees C minus, okay, the moist adiabatic lapse rate, 6 degrees C per 1,000 meters. We're going up 1,000 meters, okay, and so the air temperature will change by 6 degrees C. So our air temperature at 2,000 meters will be minus 6 degrees C. So T at 2,000 meters equals minus 6 degrees C. Okay, so that's at the top of the mountain. Now we got to take the air down, back down to the other side of the mountain. Okay, and as we do that, now we're talking about the descending side. The air is descending, and so as the air descends, it is going to, the pressure is going to increase, the air is going to compress, the density is going to increase, and so the temperature is going to warm. And so we have to ask ourselves, then, is this air going to warm at the dry adiabatic lapse rate or the moist adiabatic lapse rate? Well, if you remember earlier in this chapter, I said whenever air is descending, there's no decision to make. Descending air always warms at the dry adiabatic lapse rate. Okay, so let's see what the air temperature is going to be at 1,000 meters. So the temperature of the air at 1,000 meters as it descends down the other side will be the starting point, minus 6 degrees C. Okay, it's descending, so it's going to warm. So this time we're going to add to the temperature of the air as it descends, and this is going to warm at the dry adiabatic lapse rate, 10 degrees C per 1,000 meters, and we're going from 2,000 meters to 1,000 meters, so that's a 1,000 meter change in altitude. Okay, and so we've got minus 6 degrees C plus 10 degrees C per 1,000 meters. We're changing by 1,000 meters. So this air will warm by 10 degrees C. So the air at 1,000 meters will be at a plus 4 degrees Celsius. Okay. All right, so there we are at 4 degrees C. Temperature at 1,000 meters on the leeward side of the mountain will be a plus 4 degrees C. Now we got to take it from 1,000 meters down to the surface. And so, again, we have to ask ourselves, is this air going to warm at the dry adiabatic lapse rate or the moist adiabatic lapse rate? Again, no decision to make. Descending air is going to warm, okay, and descending air always warms at the dry adiabatic lapse rate. So let's see what the temperature of the air is going to be at the surface. So temperature of the air at the base of the mountain on the leeward side will be the starting point, 4 degrees Celsius. It's descending, so it's warming, so we're going to add. It's warming at the dry adiabatic lapse rate, 10 degrees C per 1,000 meters. Okay, and we're going from 1,000 meters down to the base of the mountain at 0 meters, so that's a distance of 1,000 meters. Okay. All right, so that will be 4 degrees C plus 10 degrees C per 1,000 meters. We're changing by 1,000 meters, and so that will be an increase of 10 degrees C. And so our temperature at the base of the mountain will be 14 degrees C. Okay, so T at 0 meters On the leeward side is 14 degrees C. All right, so notice what happens to temperature on the windward side versus leeward side. Notice the temperature of the air on the leeward side, the air warmed up. It warmed up adiabatically. And so if you ever noticed that the windward side of mountains tend to be greener and lusher because that's where the clouds and precipitation are, whereas the windward side of mountains tend to be green and lush. The leeward side tend to be kind of brown and drab and not as much precipitation. So a good example would be in Washington, in Seattle, Washington. They receive about 80 inches of precipitation per year because Seattle is on the windward side of the mountain. You look at a place like Spokane, Washington, which is on the leeward side, they only get about 16 inches of precipitation, and their temperature is a bit warmer because of the adiabatic warming that takes place. Okay, so here's an example of problem number 7, and actually it helps a little bit with problem number 3 and problem number 6 as you bring the air back down the mountain. Okay, if you have questions, let me know.